Solar fuels in the closed carbon cycle, powering civilization without emissions. Among the most audacious ideas in clean energy science is the proposition that the very gases warming our planet could become the raw material for powering it. Solar fuels, energy-dense molecules produced by harnessing sunlight to chemically transform CO2 in water, represent a potential civilizational breakthrough, a way to generate the liquid fuels that power aviation, shipping, industry, and transportation without releasing any net carbon into the atmosphere. The sun delivers more energy to Earth in a single hour than all of humanity consumes in an entire year. The atmosphere contains hundreds of billions of tons of CO2, placed there by 2 centuries of industrial combustion. Solar fuel technologies propose to close the loop, using sunlight to re-energize that CO2 back into fuel, which when burned simply returns it to the atmosphere as feedstock, completing a cycle with no net emissions and no finite resource consumption. This essay examines the science, the current state of technology, and the challenges and promise of 4 major pathways by which solar energy can be converted into fuel: green hydrogen via electrolysis, electrofuels combining hydrogen with captured CO2, artificial photosynthesis, and thermochemical solar conversion. Together, these pathways sketch a coherent vision of a post-fossil fuel energy system, one that is not merely less destructive than what we have today, but fundamentally regenerative. The logic of the closed carbon loop. To understand why solar fuels are so compelling, it helps to understand exactly what is wrong with fossil fuels at a chemical level. When we burn coal, oil, or natural gas, we are releasing carbon that was sequestered underground over millions of years, adding it as CO2 to an atmospheric carbon pool that had been in approximate equilibrium for the entirety of human civilization. This is a one-way valve. Ancient carbon flows into the atmosphere, raising its concentration, trapping heat, and destabilizing the climate systems on which life depends. Solar fuels offer an entirely different chemistry. Instead of opening that valve, they establish a cycle. Sunlight provides the energy to convert CO2 and water into hydrogen or liquid hydrocarbon fuels. Those fuels are then burned to release energy, producing CO2 and water as byproducts, but the CO2 is the same carbon that was just captured from the atmosphere to make the fuel. The net addition to the atmospheric carbon pool is zero. The sun provides all the energy, the carbon merely circulates. This is not carbon neutrality achieved through accounting tricks or offsets, it is carbon neutrality built into the fundamental chemistry of the process. This closed-loop logic is why solar fuels are qualitatively different from simply running more solar panels to generate electricity, important as that is. Electricity is difficult to store at large scale, and some of the most energy-intensive sectors of the modern economy, aviation, ocean shipping, steel production, cement manufacturing, cannot easily be electrified directly. Liquid fuels have extraordinarily high energy density. A kilogram of jet fuel contains roughly 43 megajoules of energy, compared to the best lithium-ion batteries which store around 0.7 megajoules per kilogram. Solar fuels preserve all the logistical advantages of liquid hydrocarbons: energy density, storability, transportability, compatibility with existing infrastructure, while eliminating their fatal flaw, the one-way release of fossil carbon. Green hydrogen via solar electrolysis. The most mature and commercially advanced solar fuel pathway today is green hydrogen, produced by using solar-generated electricity to split water molecules into hydrogen and oxygen through a process called electrolysis. The reaction is simple. An electrical current passed through water causes it to dissociate at 2 electrodes, releasing hydrogen gas at the cathode and oxygen at the anode. When that electricity comes from solar panels, the entire process produces no greenhouse gas emissions whatsoever. Green hydrogen is a versatile energy carrier. It can be burned directly in gas turbines or internal combustion engines, converted to electricity in fuel cells with water as the only exhaust, used as a chemical feedstock in industrial processes, or blended into existing natural gas infrastructure. The appeal is enormous. Hydrogen is the most abundant element in the universe, and its combustion product is pure water vapor. The environmental credentials are striking. Renewable energy-based green hydrogen production emits less than 2 kilograms of CO2 per kilogram of hydrogen produced, compared to 17-38 kilograms of CO2 per kilogram for hydrogen derived from fossil fuels via steam methane reforming, the current dominant production method. Research combining photovoltaic and concentrated solar thermal inputs with advanced electrolyzers has demonstrated material efficiency of nearly 95% and environmental efficiency above 98%, reducing CO2 emissions by approximately 88% compared to hydrogen produced using grid electricity. The principal challenge facing green hydrogen is not chemistry but physics and economics. Hydrogen has very low volumetric energy density in its gaseous state. A tank of hydrogen at ambient pressure contains very little energy compared to the same volume of liquid gasoline or diesel. Compression to high pressure, or liquefaction to cryogenic temperatures, addresses this but adds energy costs and infrastructure complexity. Hydrogen also embrittles metal pipelines over time, complicating its use in existing natural gas networks. These challenges are real, but they are engineering problems with engineering solutions, problems of cost and scale, not of fundamental feasibility. The economic trajectory is strongly encouraging. The cost of solar photovoltaic electricity has fallen by more than 90% over the past 15 years, and electrolyzer costs are following a similar learning curve as manufacturing scales up. The U.S. Department of Energy has targeted a green hydrogen cost of $1 per kilogram by 2031, a threshold that would make it cost competitive with fossil-derived hydrogen and open vast new markets. At that price point, green hydrogen becomes viable not just as a fuel but as a universal chemical feedstock capable of decarbonizing industries from fertilizer production to steel manufacturing. Electrofuels, combining solar hydrogen with captured CO2. Because hydrogen's storage and transport challenges limit its direct use as a fuel, the most commercially promising near-term solar fuel pathway combines green hydrogen with captured CO2 to produce energy-dense liquid molecules, electrofuels, or F-fuels, that are chemically identical or equivalent to conventional petroleum products and can be used in existing engines, pipelines, and infrastructure with no modification. The production chain has 3 stages. First, CO2 is captured, either from the atmosphere via direct air capture technology, or from concentrated industrial point sources like power plants, cement kilns, or steel mills where CO2 concentrations are high enough to make capture significantly cheaper. Second, water is electrolyzed using solar electricity to produce green hydrogen. Third, the hydrogen and CO2 are combined through catalytic synthesis processes, most commonly Fischer-Tropsch synthesis or methanol synthesis, to produce the desired liquid fuel product. The chemistry of F-fuel synthesis is well established. It is essentially the reverse of combustion. Methanol can be produced directly from hydrogen and CO2 via the reaction CO2 plus 3H2CH3O plus H2O. Longer chain hydrocarbons, diesel, kerosene, gasoline, are produced via Fischer-Tropsch synthesis, which first converts CO2 and hydrogen into synthesis gas, a mixture of carbon monoxide and hydrogen, and then polymerizes this into hydrocarbon chains of various lengths. The product can be tuned to match any petroleum fuel specification. The practical implications are transformative. Aviation is among the hardest sectors to decarbonize because jet aircraft require high energy density fuels that batteries cannot provide at any foreseeable technology level. Synthetic kerosene, chemically identical to conventional jet A fuel, can power existing aircraft with zero net carbon emissions when produced from solar energy and atmospheric CO2. The same logic applies to shipping. Synthetic methanol and synthetic diesel can power the world's cargo fleet without redesigning engines or rebuilding port infrastructure. Porsche has already initiated F-fuel production in southern Chile, where world-class wind resources generate cheap electricity for electrolysis, with ambitions to produce 550 million liters annually before 2030. HIF Global, Carbon Recycling International, and dozens of other companies are racing to scale similar facilities. The carbon arithmetic is elegant. When synthetic kerosene made from atmospheric CO2 is burned in a jet engine, the CO2 released is the same carbon just removed from the atmosphere to make the fuel. The net atmospheric CO2 balance is zero. The entire energy content of the fuel, and thus of the aircraft's motion, was delivered by sunlight. This is what a zero-emission aviation system actually looks like, not the elimination of liquid fuels, which is physically impractical for aircraft, but the transformation of their production into a solar-powered, closed-carbon process. Artificial photosynthesis, the solar fuel holy grail. While electrofuel production chains are already commercial at pilot scale, the longer-term scientific frontier is artificial photosynthesis, devices that, like a leaf, convert sunlight, water, and CO2 directly into fuel in a single integrated process, with no electricity generation as an intermediate step. Natural photosynthesis is the process by which plants, algae, and cyanobacteria use sunlight to drive the conversion of CO2 and water into sugars and oxygen. It is, in a sense, the original solar fuel technology, and it has powered the biosphere for over 3 billion years. But natural photosynthesis is remarkably inefficient at capturing solar energy. Most plants convert only about 1% of incident sunlight into chemical energy. Artificial photosynthesis aims to replicate the essential chemistry at far higher efficiency using purpose-designed materials and catalysts, producing not sugars but directly useful fuels, hydrogen, methanol, or synthetic hydrocarbons. The fundamental challenge is that useful fuel synthesis requires multiple electron transfers, multiple light-driven chemical steps that must be coordinated within a single molecular or material system. For decades, this multi-step requirement was the primary obstacle. Researchers could drive individual reactions photochemically, but linking them together efficiently proved enormously difficult. A significant breakthrough was published in Nature Chemistry in August 2025. Researchers developed a specially structured 5-part molecule with a light-sensitive core. When light strikes this core, one side of the molecule releases an electron, establishing simultaneously both a positive and a negative charge, a configuration that can drive the multi-step chemistry of water splitting and CO2 reduction. The ability to store 2 positive and 2 negative charges simultaneously in a single molecular structure removes a fundamental architectural constraint that had blocked practical artificial photosynthesis for decades. Solar-driven CO2 reduction mimics natural photosynthesis by harnessing sunlight to convert water and CO2 into chemicals, enabling the storage of solar energy in energy-dense molecules for on-demand use. The promise is a device with no moving parts, no electrolyzers, no separate CO2 capture units, just sunlight going in and fuel coming out, in a process as self-contained as a leaf. Such devices could theoretically be deployed at enormous scale: artificial solar fuel farms covering desert land, floating panels on reservoirs, or building integrated surfaces converting sunlight directly into the liquid fuels needed by the adjacent community. Honesty requires acknowledging the current limitations. Current solar-driven CO2 reduction platforms remain well below the efficiency and cost thresholds necessary for commercial-scale deployment. The gap between laboratory demonstration and industrial implementation is vast, and the history of energy technology is littered with breakthroughs that proved harder to scale than anticipated. Nevertheless, the 2025 molecular breakthrough represents genuine scientific progress, and the convergence of advances in photocatalyst design, nanostructured materials, computational chemistry, and reactor engineering is accelerating the field rapidly. Thermochemical solar fuels. A fourth pathway exploits not sunlight's photonic energy but its thermal energy, using concentrated solar power, CSP, arrays of mirrors focusing sunlight onto a central receiver, to generate temperatures exceeding 1000 degrees Celsius. At these extreme temperatures, CO2 and water can be split thermochemically through metal oxide redox cycles, producing carbon monoxide, CO and hydrogen, syngas, without any electricity as an intermediate. This syngas is then catalytically converted to liquid fuels via Fischer-Tropsch synthesis. The thermochemical route uses the full solar spectrum. Unlike photovoltaics, which only efficiently capture certain wavelengths, it can achieve high theoretical efficiencies and produces fuels at high temperature and pressure that are already well suited to downstream catalytic processing. The Swiss Federal Institute of Technology, ETH Zurich, and the German Aerospace Center, DLR, have built and operated pilot-scale solar thermochemical reactors, demonstrating the scientific viability of the approach. Scale-up requires advances in materials that can withstand repeated thermal cycling at extreme temperatures, and in reactor engineering to minimize heat losses. Thermochemical solar fuels are likely to be most competitive in sun-rich regions with abundant desert land, the Middle East, the Sahara, the American Southwest, the Atacama, where concentrated solar power is most economical and where the combination of cheap solar heat, available land, and proximity to CO2 point sources or direct air capture facilities creates favorable conditions. The integrated system. What a solar fuel economy looks like. Drawing the four pathways together, a mature solar fuel economy would look something like this: vast solar farms in high-radiance regions, deserts, offshore platforms, repurposed land, generate electricity at very low cost. A portion of this electricity directly powers grids via transmission lines. The remainder drives electrolyzers producing green hydrogen. That hydrogen is combined with CO2 captured from industrial facilities or directly from the atmosphere, and converted via established catalytic chemistry into green methanol, synthetic diesel, kerosene, or ammonia. These fuels flow into existing global supply chains, tankers, pipelines, fueling stations, infrastructure already worth trillions of dollars that requires no modification. Aircraft fly on synthetic kerosene. Container ships run on green methanol. Trucks and buses use synthetic diesel or hydrogen fuel cells. Industrial processes that require high-temperature heat, cement, steel, glass, chemicals, are powered by synthetic fuels or direct hydrogen combustion. Agricultural fertilizer, currently produced from fossil-derived hydrogen at the cost of enormous emissions, is manufactured from green hydrogen and atmospheric nitrogen. Every combustion event returns CO2 and water to the atmosphere or industrial streams, where it is immediately recaptured as feedstock for the next batch of fuel. CO2 capture technologies integrated with solar-based hydrogen production could reach commercially viable scale within decades, with over 5 billion tons of CO2 potentially utilized for clean fuel production worldwide by 2050, a quantity comparable to a significant fraction of current global emissions. AI-assisted optimization of carbon capture systems is already reducing costs by up to 40%, and continued advances in catalyst design, electrolyzer efficiency, and process integration are compressing the timeline toward commercial competitiveness. Challenges and caveats. This vision is scientifically coherent and technologically grounded, but the challenges are substantial and must be stated plainly. The energy efficiency of the full fuel production chain, from solar panel to liquid fuel, is currently low. Roughly speaking, about 15 to 20% of the solar energy captured ends up in the final liquid fuel, with losses at each conversion step. This means that producing fuels requires roughly 5 to 7 times more solar capacity than simply using solar electricity directly. Since solar panels are now cheap, this is less of a fatal objection than it once seemed, but it does mean that solar fuel production requires enormous land and capital investment. Direct air capture of CO2, while technically proven, remains expensive, currently around $300 to $500 per ton of CO2 captured, compared to the roughly $50 to $100 per ton that would make it broadly economical. Costs are falling rapidly as the industry scales, but the trajectory needed to reach cost-competitive fuels within the 2030s requires sustained investment and policy support that is far from guaranteed. Green hydrogen costs need to fall substantially. The $1 kg target is achievable but not yet reached. Electrolyzer manufacturing must scale by orders of magnitude. Fischer-Tropsch catalysts must be made more selective and durable. The enormous infrastructure build required, new electrolyzers, CO2 pipelines, synthesis plants, demands capital investment comparable to the fossil fuel infrastructure it replaces. None of these challenges are insurmountable, but each requires time, investment, and policy frameworks that internalize the true cost of carbon. The sun as the last energy source we will ever need. There is something philosophically profound about solar fuels. For the entirety of the fossil fuel era, human civilization has been spending a finite inheritance, the solar energy stored underground over geological time, and will eventually exhaust it. Solar fuels represent a different relationship with energy entirely, not mining the past but harvesting the present, using the sun's continuous output as the energy source for an indefinitely sustainable civilization. The closed carbon loop is not merely an engineering achievement, it is a conceptual reorientation, from a linear economy that extracts, uses, and discards, to a circular one where carbon, water, and sunlight cycle endlessly through fuels, combustion, capture, and resynthesis. The atmosphere becomes not a dump for industrial waste but a vast reservoir of raw material, a feedstock commons that replenishes itself as fast as it is drawn upon. The science is sound, the chemistry is understood. The engineering challenges, while real, are of the kind that human ingenuity and industrial investment have repeatedly overcome. What remains is the political commitment to price carbon honestly, to fund the research and infrastructure that solar fuel technologies require, and to recognize that the energy transition is not merely a matter of installing more solar panels and wind turbines, but of reinventing the entire chemistry of civilization. The sun has been burning for 5 billion years and will burn for 5 billion more. It is time to learn, at last, to run our world on the light it gives us freely every day. How can we turn solar energy into fuel to power everything with no emissions, and by using greenhouse gases as feedstocks? We can achieve this through solar fuels or e-fuels, also called electrofuels or power-to-X technologies, which use solar energy to convert greenhouse gases, primarily CO2, and sometimes CH4, into carbon-neutral synthetic fuels like methane, methanol, gasoline, diesel, or jet fuel. These fuels are drop-in replacements for fossil fuels, powering transportation, aviation, shipping, heavy industry, and even electricity generation, via gas turbines or fuel cells, while producing net zero emissions in a closed carbon loop. The core idea mimics, but improves on natural photosynthesis. Solar energy drives the reduction of CO2, captured from the air or point sources, with water, storing energy in chemical bonds of fuels. When the fuels are burned, they release the same CO2 that was captured, which is then recaptured, resulting in no net emissions. This recycles atmospheric greenhouse gases as feedstocks instead of letting them accumulate. Most scalable pathway today, e-fuels, indirect solar route via green hydrogen. This is the leading commercial approach, already in pilot plants. Step 1. Solar electricity generation. Solar photovoltaic, PV panels, or concentrated solar, produce clean electricity. Step 2. Green hydrogen production. Electricity powers water electrolysis, splitting H2O into H2 and O2. This green H2 is the energy carrier. Step 3. CO2 capture as feedstock. Use direct air capture, DAC, to pull CO2 directly from ambient air, or capture from biogenic industrial sources. This is the greenhouse gas feedstock. Step 4. Fuel synthesis. Catalysts combine H2 and CO2, methanol synthesis, CO2 plus 3H2CH3O plus H2O, then upgrade to gasoline. Sabatier reaction, CO2 plus 4H2CH4, synthetic natural gas, plus 2H2O, reverse water gas shift plus Fischer-Tropsch, produces syngas, CO plus H2, then liquid hydrocarbons, e-diesel, e-kerosene, e-gasoline. These are fully compatible with existing engines, pipelines, and infrastructure. Net zero emissions. The CO2 released on combustion equals what was captured from the atmosphere. No new fossil carbon is added. Excess renewable electricity can be stored as fuel for later use anywhere. Companies and projects, in Europe, with partners like GE Vernova, are scaling this, using solar wind for electrolysis and DAC. It's energy intensive but costs are falling with cheaper solar and better electrolyzers. Emerging direct solar routes, artificial photosynthesis and solar thermochemistry. These use sunlight directly for higher theoretical efficiency, integrating capture and conversion in one device. Photocatalytic photoelectrochemical, PC systems, artificial leaves, semiconductors or hybrid catalysts, metal oxides, MOFs, perovskites, or Z-scheme materials like Ag2STO2, absorb sunlight. They split water, oxidation while reducing CO2, with electrons protons, into fuels like syngas, CO plus H2, methane, methanol, formate, or ethylene. Example, University of Cambridge's 2025 solar-powered flow reactor. Specialized filters capture CO2 from air at night, like a sponge. Sunlight heats the CO2, infrared absorption, while a semiconductor powder absorbs UV to trigger conversion to solar syngas. A mirror concentrates light for efficiency. No external power, cables, or batteries needed. Researchers are scaling it to produce liquid fuels for cars, planes. NASA's thin-film photoelectrochemical device uses inexpensive metal oxide films, titanium dioxide composites, to convert industrial CO2 directly into methane or other fuels with sunlight across UV visible IR spectra. Compact, low-cost, zero-carbon footprint recycling. Solar thermochemical, concentrated solar power, mirrors concentrate sunlight to high temperatures, 1000 degrees Celsius. Redox materials, metal oxides, cycle between oxidized reduced states to split H2O and CO2 into H2 and company, syngas, in a two-step thermochemical loop. Syngas is then converted to fuels via standard catalysis. EDH Zorex Solar Mini Refinery demonstrates this, producing 100 milliliters of CO2-neutral fuel methanol, petrol, diesel, kerosene, per day in a rooftop prototype. These direct methods are advancing rapidly in labs, efficiencies improving to several percent solar to fuel, with high selectivity, but they're earlier stage than fuels. Why this powers everything with no emissions. Universal fuels, synthetic hydrocarbons are energy-dense, storable, transportable, and work in existing infrastructure, unlike pure electricity or H2 alone for hard-to-electrify sectors, aviation, shipping, long-haul trucking, chemicals. Closed carbon cycle, CO2 is both feedstock and combustion product. Atmospheric levels stabilize or drop if scaled with DEC. Scalability, solar is abundant, pair with DEC for truly air-derived fuels. Decentralized reactors, like Cambridge's, could work off-grid. Co-benefits, reduces air pollution, creates jobs in green tech, and turns a pollutant into a resource. Challenges and outlook, current costs are higher than fossil fuels, but solar prices keep dropping, and efficiency selectivity are rising fast, better catalysts suppress side reactions. Pilots are operating, full commercialization is expected in the 2030s with policy support, carbon pricing, mandates. This is not science fiction, it's engineering a circular, emission-free energy economy using the sun and recycled CO2. With investment, it can replace fossil fuels comprehensively. The process of converting solar energy into fuels while using greenhouse gases as feedstocks operates through engineered chemical cycles that store solar energy in the bonds of synthetic hydrocarbons or alcohols. These cycles recycle carbon dioxide CO2 captured from the atmosphere or industrial sources, ensuring that the fuels produce no net emissions when burned because the released CO2 matches exactly what was originally captured. The overall transformation begins with abundant sunlight as the sole energy input and water as a hydrogen source, ultimately yielding drop-in fuels such as methane, methanol, or liquid hydrocarbons that power every sector of the economy, from cars and airplanes to power plants and chemical manufacturing, within a completely closed carbon loop. The most established and scalable version of this process follows the indirect fuels or power-to-X pathway, which uses solar-generated electricity as an intermediate energy carrier before synthesizing the fuel. In the first stage, photovoltaic panels or concentrated solar power systems absorb sunlight across large arrays and convert it directly into electricity through the photovoltaic effect, where photons excite electrons in semiconductor materials such as silicon to generate a flow of current. This electricity then drives water electrolysis and specialized electrolyzers, typically proton exchange membrane or alkaline types. During electrolysis, an electric current passes through water, often with a small amount of electrolyte for conductivity, splitting it at the electrodes according to the reaction to H2O to H2 plus O2. At the cathode, protons gain electrons to form hydrogen gas, while at the anode, water molecules lose electrons to produce oxygen gas and protons. The resulting green hydrogen serves as a high-energy carrier that stores the solar electricity in chemical form without any carbon emissions. Next, carbon dioxide is captured as the primary greenhouse gas feedstock through direct air capture systems. These units draw in ambient air using large fans and pass it over chemical sorbents, such as amine-based liquids or solid porous materials like metal organic frameworks, that selectively bind CO2 molecules via weak chemical bonds or physical adsorption. Once saturated, the sorbent is heated or subjected to a pressure swing, using some of the solar-derived energy to release a concentrated stream of pure CO2 while regenerating the sorbent for continuous operation. This step pulls existing atmospheric CO2 into the process, preventing its accumulation and turning a climate pollutant into a valuable raw material. With green hydrogen and captured CO2 in hand, the final synthesis stage employs catalytic reactors to combine them into usable fuels. In one common route for methanol production, the gases react over copper-zinc oxide catalysts at moderate temperatures, around 200 to 300 degrees Celsius, and pressures, 50 to 100 bar via the exothermic reaction CO2 plus 3H2CH3O plus H2O. For synthetic methane, the Sabatier reaction occurs over nickel-based catalysts at similar conditions, CO2 plus 4H2CH4 plus 2H2O, to produce longer-chain liquid fuels such as a diesel or a kerosene. The process first performs a reverse water gas shift reaction, CO2 plus H2CO plus H2O to generate carbon monoxide, forming syngas, a mixture of CO and H2. This syngas then feeds into Fischer-Tropsch synthesis reactors, where iron or cobalt catalysts at 200 to 350 degrees Celsius and elevated pressure polymerize the molecules into hydrocarbons ranging from C5 to C20 chains according to the general stoichiometry NCO plus, 2N plus 1, H2CH22 plus and H2O. The resulting fuels are chemically identical to their fossil counterparts, so they burn cleanly in existing engines and turbines, releasing only water vapor and the original captured CO2, which is then recaptured to restart the cycle. Excess heat or byproducts from these exothermic reactions can be recovered to improve overall efficiency, and the entire chain can run on intermittent solar power by storing hydrogen or electricity in buffers. In parallel, emerging direct solar conversion routes eliminate the electricity intermediate and harness sunlight photons immediately to drive the chemistry, often achieving higher theoretical efficiencies by avoiding conversion losses. One such approach is artificial photosynthesis, implemented in photoelectrochemical cells or photocatalytic reactors that function like engineered leaves. Here, specialized semiconductor materials, such as titanium dioxide modified with copper or perovskite layers, or Z-scheme heterostructures combining multiple photocatalysts, absorb photons across the solar spectrum. Upon absorption, electrons are excited from the valence band to the conduction band, creating electron-hole pairs. The holes oxidize water at one site, 2H2O2 plus 4H plus 4E to the power of negative, while the electrons reduce CO2 at another site through multi-electron transfer steps. For example, CO2 can be reduced stepwise to carbon monoxide, CO2 plus 2H plus 2E to the power of negative CO plus H2O, or further to methane, CO2 plus 8H plus 8E to the power of negative CH4 plus 2H2O, with protons shuttled through the system to maintain charge balance. Advanced designs incorporate gas diffusion electrodes, or flow reactors that capture dilute CO2 directly from air overnight via sorbent layers, then activate the photocatalyst under concentrated sunlight during the day. No external wires or batteries are required. The device self-powers through light-driven charge separation, producing fuels such as syngas, methanol, or formate with selectivities tuned by catalyst composition to suppress unwanted side products like hydrogen gas. The other direct route, solar thermochemistry, relies on concentrated solar power towers or parabolic dishes that focus sunlight to heat a reactor to temperatures exceeding 1000 degrees Celsius. Redox active metal oxides, commonly ceria, CO2, or perovskite structured materials, undergo a two-step thermochemical cycle. In the high-temperature reduction step, solar heat drives oxygen release from the oxide lattice, MOMO plus Greek letter delta 2O2, creating oxygen vacancies. In the lower temperature oxidation step, still above 800 degrees Celsius but cooler than reduction, these vacancies react with CO2 or H2O. The material reoxidizes by splitting the feedstock, CO2 CO plus O2 incorporated into the lattice, or H2O H2 plus O2. The net result is syngas, CO plus H2 produced purely from heat, water, and CO2, without electricity. This syngas then enters the same catalytic upgrading steps as in the F-Fuels pathway to form liquid hydrocarbons. The cycle repeats continuously as the redox material shuttles between states, and the high temperatures enable rapid kinetics and high solar to fuel efficiencies by utilizing the entire solar spectrum as thermal energy rather than just photons. Across all pathways, system integration ensures net zero emissions by maintaining a closed carbon balance. Every molecule of CO2 incorporated into the fuel originates from the atmosphere or recycled sources, so combustion simply returns it without adding new greenhouse gases. Process efficiencies vary. F-Fuels currently achieve 50 to 70% electricity to fuel conversion, with overall solar to fuel around 10 to 20% depending on solar input, while direct methods target 10 to 30% in optimized prototypes. But ongoing catalyst improvements, better heat recovery, and larger-scale solar deployment continue to drive costs downward. Water consumption is managed through recycling or seawater desalination powered by the same solar arrays, and modular reactor designs allow deployment near solar resources or demand centers. In full operation, these processes enable a fully renewable, emission-free energy economy by transforming intermittent sunlight and waste CO2 into storable, transportable fuels that replace every fossil application without infrastructure overhaul or atmospheric impact. How solar fuels work, a complete technical explanation. The starting point, why liquid fuels are hard to replace. Before tracing the process step by step, it is worth understanding why solar fuels are necessary at all, rather than simply replacing everything with batteries and electric motors. The answer lies in energy density. A kilogram of jet fuel contains roughly 43 megajoules of chemical energy. The best lithium-ion batteries available today store around 0.7 megajoules per kilogram, about 60 times less. For a long-haul aircraft, this gap is decisive. A battery-powered plane carrying the same passengers over the same distance as a conventional jet would need to carry so much battery mass that the basic physics of flight breaks down. The same logic applies to ocean-going cargo ships, which cross thousands of miles of open water, and to industrial furnaces that must maintain temperatures above 1,500 degrees Celsius for hours or days at a time. These sectors, aviation, shipping, high-temperature industry, cannot wait for batteries to catch up. They need liquid fuels, or something chemically equivalent. Solar fuels provide exactly that, the same energy-dense molecules, produced without fossil carbon. Step 1. Capturing sunlight and converting it to electricity. Everything in the solar fuel chain begins with photons, particles of light emitted by the sun and traveling 150 million kilometers to reach Earth's surface. When these photons strike a solar photovoltaic cell, they interact with a semiconductor material, most commonly silicon. Silicon atoms are arranged in a crystal lattice, and their electrons occupy defined energy levels. When a photon of sufficient energy strikes a silicon atom, it knocks an electron free from its position in the lattice and promotes it to a higher energy state where it is free to move. The solar cell is constructed with a deliberate asymmetry, a junction between two layers of silicon doped with different impurities, that creates an internal electric field. This field acts like a one-way valve, sweeping the liberated electrons in one direction and the positively charged holes they leave behind in the other. The separation of these charges creates a voltage difference across the cell, and when the cell is connected to an external circuit, electrons flow through it as electrical current. This is the photovoltaic effect, and it is the foundational process by which sunlight becomes electricity. In a modern utility-scale solar farm, thousands of these cells are connected in series and parallel within panels, and thousands of panels are mounted across acres of land. The electricity they generate is direct current, which is converted to alternating current by inverters and fed into the grid or, in the case of solar fuel production, directed straight to the electrolysis facility next door. The efficiency of commercial silicon solar panels, the fraction of incident solar energy converted to electricity, currently sits between 20 and 24%, with the theoretical maximum for silicon around 29%. Newer perovskite and tandem cell designs are pushing efficiencies above 30% in laboratory settings, and these advances directly improve the economics of every downstream solar fuel process. Step 2. Splitting water with electricity, the electrolysis of water. The electricity generated by the solar farm is directed to an electrolyzer, which uses it to split water molecules into their constituent elements, hydrogen and oxygen. This is electrolysis, and it is worth understanding in some chemical detail, because hydrogen is the universal intermediate in all solar fuel pathways. Water, H2O, is a stable molecule. Its hydrogen and oxygen atoms are held together by covalent bonds, meaning they share electrons. Breaking these bonds requires an input of energy. In an electrolyzer, that energy comes from electricity. The device consists of two electrodes immersed in water or a water-based electrolyte solution, connected to a power supply. The negative electrode is called the cathode, and the positive electrode is called the anode. When electricity flows, a series of electrochemical reactions occur simultaneously at both electrodes. At the cathode, electrons arriving from the power supply combine with hydrogen ions, protons, H, present in the water to form hydrogen gas. The reaction is 2H plus 2e to the power of negative H2. Hydrogen bubbles form and rise from the cathode surface. At the anode, water molecules are oxidized, they lose electrons to the electrode, and are broken apart into oxygen gas and protons. The reaction is 2H2O2 plus 4H plus 4e to the power of negative. Oxygen bubbles rise from the anode. The protons released at the anode migrate through the electrolyte toward the cathode to participate in further hydrogen production, maintaining the electrical balance of the system. The two most commercially important electrolyzer types are alkaline electrolyzers and proton exchange membrane, PEM electrolyzers. Alkaline electrolyzers use a liquid potassium hydroxide solution as the electrolyte and have been deployed industrially for over a century. They are durable and relatively cheap to manufacture, but they are large and respond slowly to changes in power input, a limitation when paired with variable solar generation. PEM electrolyzers use a solid polymer membrane as the electrolyte. Protons pass through the membrane from anode to cathode, while electrons travel the external circuit. PEM electrolyzers are compact, respond rapidly to fluctuating power input, and produce extremely pure hydrogen, making them the preferred technology for coupling with solar farms, where power output varies with cloud cover and time of day. The primary disadvantage of PEM electrolyzers is that their membranes and catalysts use platinum group metals, which are expensive and geologically scarce, a significant constraint on the scale of deployment needed for a solar fuel economy. Solid oxide electrolyzers, a third type that operates at very high temperatures, 700 to 900 degrees Celsius, offer the highest theoretical efficiency but are still in earlier stages of commercial development. The output of the electrolyzer is a stream of gaseous hydrogen, which is then compressed, cooled, and either stored or immediately piped to the fuel synthesis facility. Step 3. Capturing carbon dioxide from the air or industrial sources. Hydrogen alone is a fuel. It burns cleanly in air, producing only water vapor, but its very low volumetric density makes it difficult to store and transport at the scales needed for aviation, shipping, and industrial use. The solution is to combine the hydrogen with carbon dioxide to form denser liquid molecules. This requires a supply of CO2, and there are two primary sources: point source capture from industrial facilities, and direct air capture from the atmosphere. Point source capture is more economical. Facilities that already concentrate CO2 in their exhaust streams, coal and gas power plants, cement kilns, steel blast furnaces, ethanol fermentation plants, can install carbon capture equipment that separates CO2 from the other gases in their flue stream before they are vented to the atmosphere. The most widely used method is chemical absorption using amine solvents, typically monoethanolamine, MEA. The hot exhaust gas is passed through a liquid amine solution, which chemically reacts with unbind CO2 molecules, allowing the other gases, nitrogen, water vapor, residual oxygen, to pass through unabsorbed. The CO2-laden amine solution is then pumped to a separate vessel where it is heated with steam, causing it to release the CO2 as a concentrated gas stream. The regenerated amine is recycled back to absorb more CO2, and the purified CO2 stream is compressed for transport or use. Direct air capture, DAC, is more technically challenging because CO2 in the atmosphere is present at only about 420 parts per million, a much lower concentration than in industrial flue gases, which can run to 10 to 15%. Moving the enormous volumes of air needed to capture meaningful quantities of CO2 requires large fans and substantial electricity consumption. DAC systems also use solid or liquid sorbents that chemically bind CO2 at ambient temperature and then release it when heated. The most advanced commercial DAC plants, operated by companies like Limiworks in Iceland and Carbon Engineering in Canada, currently capture CO2 at cost between $300 and $500 per ton. But engineering analyzes project that cost could fall to $100 per ton or below as the technology scales, a threshold at which DAC-derived CO2 becomes economically viable as a feedstock for fuel production. In a fully realized solar fuel system, all CO2 used as feedstock would ideally come from direct air capture, because this ensures that the carbon in the final fuel was genuinely removed from the atmosphere, making the entire combustion and recapture cycle truly carbon neutral at a planetary scale. Using CO2 from point sources is valuable as an intermediate step, but it does not directly reduce atmospheric CO2 concentrations, it merely delays the release of carbon that would have been emitted anyway. Step 4. Synthesizing liquid fuels from hydrogen and CO2. With a supply of green hydrogen and captured CO2, the next step is to combine them chemically to form the desired liquid fuel product. There are several synthesis routes, each producing a different class of fuel molecule. Methanol synthesis is the simplest and most direct. Methanol, CH3O, is a liquid alcohol that can be used directly as a fuel in adapted internal combustion engines, blended into gasoline, burned in fuel cells, or used as a chemical feedstock for making other materials. The synthesis reaction is CO2 plus 3H2CH3O plus H2O. This reaction is thermodynamically favorable under moderate conditions, temperatures of 200 to 300 degrees Celsius and pressures of 50 to 100 atmospheres, in the presence of a copper and zinc oxide catalyst. The reaction is exothermic, meaning it releases heat as the bonds form, which can be recovered and used elsewhere in the process to improve overall efficiency. The methanol produced is separated from unreacted gases and water by cooling and condensation, then purified by distillation. Fischer-Tropsch synthesis produces longer-chain hydrocarbons, molecules more closely resembling conventional diesel, kerosene, and gasoline, and is therefore most relevant for aviation and marine fuels, where methanol's lower energy density is a disadvantage. The process works in two stages. First, CO2 and hydrogen are converted to synthesis gas, syngas, a mixture of carbon monoxide, CO and hydrogen, via the reverse water gas shift reaction, CO2 plus H2CO plus H2O. This reaction requires a temperature of 300 to 400 degrees Celsius and a suitable catalyst, typically iron or cobalt. Second, the syngas is fed into the Fischer-Tropsch reactor, where the CO and H2 molecules are polymerized over an iron or cobalt catalyst at 150 to 350 degrees Celsius and 10 to 40 atmospheres to form a distribution of hydrocarbon chains of varying lengths, from light gases, methane, propane, to heavy waxes. The specific distribution of chain lengths depends on temperature, pressure, the hydrogen to CO ratio, and the choice of catalyst. Lower temperatures in cobalt catalysts favor longer chains, waxes in diesel, higher temperatures in iron catalysts favor shorter chains, gasoline and jet fuel. The wax fraction can be hydrocracked, broken apart using hydrogen at high temperature, to produce additional diesel and jet fuel. The final products are molecularly identical to their petroleum-derived counterparts and require no modification of engines, fuel systems, or infrastructure. Ammonia is a fourth product worth mentioning because of its dual role as an industrial chemical and a potential fuel. Ammonia, NH3, is currently produced in enormous quantities, over 180 million tons per year, via the Haber-Bosch process, which combines hydrogen derived from natural gas with nitrogen from the air, consuming about 1 to 2% of global energy and emitting correspondingly large quantities of CO2. Green ammonia replaces the fossil-derived hydrogen with electrolytic green hydrogen, using the same synthesis chemistry, N2 plus 3H22NH3, at 400 to 500 degrees Celsius and 150 to 300 atmospheres over an iron catalyst. Green ammonia can decarbonize fertilizer production entirely and is also being developed as a zero-carbon shipping fuel, since it burns without releasing CO2 and has adequate energy density for marine applications. Step 5. The combustion event, energy releasing the return of CO2. When a synthetic fuel produced by the process described above is burned, whether in a jet engine, a marine diesel, a gas turbine, or a furnace, the stored chemical energy is released as heat and mechanical work. Hydrocarbon combustion follows the same chemistry regardless of whether the fuel was made from fossil carbon or from atmospheric CO2. The reaction of a hydrocarbon with oxygen in air produces CO2 and water. For methanol, for example, 2CH3O plus 3O2 2CO2 plus 4H2O. For a kerosene equivalent fuel like dodecane, C12H26 plus 18.502 12 CO2 plus 13 H2O. The critical point is what happens to that CO2. When fossil fuel burns, the CO2 it releases was locked underground for tens of millions of years. It is genuinely new carbon entering the atmospheric pool, where it will persist for centuries to millennia. When solar-derived synthetic fuel burns, the CO2 it releases was drawn from the atmosphere, perhaps days or weeks earlier, to make that very fuel. The atmospheric CO2 concentration is entirely unaffected. The carbon has simply made one trip around the cycle: atmosphere capture, synthesis, combustion, atmosphere. The net effect on the climate is zero. Step 6. Closing the loop, recapture and recycling. For the system to be genuinely closed, the CO2 emitted during combustion must be captured and returned to the synthesis facility as feedstock. In practice, this is easiest for stationary combustion sources, power plants, industrial furnaces, and fuel synthesis plants themselves, where capture equipment can be permanently installed. For mobile sources like aircraft and ships, the CO2 is emitted into the atmosphere in dispersed form, and must be recaptured by direct air capture at centralized locations. This is why the expansion of that capacity is so fundamental to the solar fuel vision. It is the mechanism by which dispersed atmospheric CO2, from aircraft exhaust 30,000 feet overhead, from ship funnels in mid-ocean, from industrial smokestacks around the world, is reconcentrated and returned to the synthesis process. In a mature system, DAC facilities would be co-located with solar farms and electrolyzers, forming integrated solar fuel production complexes that take in sunlight, water, and atmospheric CO2, and output liquid fuels. The only material inputs to the system are solar radiation, water, which is regenerated during combustion and can be captured and recycled, and the nitrogen, steel, silicon, and polymers embodied in the equipment itself. The only significant energy input is sunlight. The carbon circulates indefinitely without accumulating in the atmosphere. The efficiency cascade, where energy is lost along the way. An honest account of the solar fuel process must trace the energy losses that accumulate at each conversion step, because these determine how much solar capacity is needed to deliver a given quantity of final fuel. Starting from 100 units of incident solar energy, a commercial solar panel captures and converts roughly 22 units to electricity, losing the rest as heat into photons whose energy does not match silicon's absorption band. The electrolyzer converts roughly 70 to 80% of that electricity to chemical energy stored in hydrogen bonds, yielding approximately 16 units of hydrogen energy. The CO2 capture process consumes some of that energy, roughly 1-2 units, reducing the hydrogen available for synthesis. The Fischer-Tropsch methanol synthesis step converts hydrogen to liquid fuel at about 60 to 70% efficiency, yielding perhaps 10 units of chemical energy in the final fuel. Compression, cooling, transport, and distribution consume additional fractions. The net result is that the fuel production chain, from sunlight to liquid fuel in a tank, achieves an overall solar-to-fuel efficiency of roughly 10 to 15%. This means that producing 1 unit of fuel energy requires capturing 6 to 10 units of solar energy. This sounds inefficient, and in absolute terms it is, but it must be compared against the alternative. Fossil fuels are extracted from the ground at high energy cost, refined in enormously energy-intensive processes, and transported globally, all before any useful combustion occurs. Their efficiency is deceptively high only because the energy of ancient photosynthesis is not counted. And critically, solar energy is available in quantities that dwarf human civilization's total energy needs. Covering a modest fraction of the world's desert land with solar panels, less than 1%, would generate sufficient electricity to produce all the synthetic fuel required to power global aviation, shipping, and heavy industry at current levels. The role of artificial photosynthesis, collapsing the chain. The multi-step process described above, solar electricity, electrolysis, CO2 capture, synthesis, involves several distinct facilities, each with its own capital cost and conversion loss. Artificial photosynthesis represents the scientific aspiration to collapse all of these steps into a single device, a material or molecular system that, like a plant leaf, absorbs sunlight directly and uses that energy to drive the reduction of CO2 and the oxidation of water simultaneously, producing fuel molecules in a single integrated process. The fundamental chemistry of artificial photosynthesis involves photocatalysis. A photocatalyst is a material that absorbs light and uses the resulting electronic excitation to drive chemical reactions that would otherwise be thermodynamically uphill. In water splitting, the photocatalyst must absorb a photon, generate a free electron in an electron hole, use the hole to oxidize water at one catalytic site, producing oxygen, and use the electron to reduce protons at another site, producing hydrogen. In CO2 reduction, the electron is instead used to reduce CO2 to CO, formic acid, methanol, or other carbon compounds, depending on how many electrons are transferred and what catalytic sites are present. The central challenge is that these multi-electron reactions require the coordinated management of multiple charges simultaneously, and most molecular systems either recombine those charges before useful chemistry occurs, or lack the thermodynamic driving force to complete all the required steps. The 2025 breakthrough molecule addresses this by building charge separation directly into a multifunctional molecular architecture, a light-absorbing center flanked by electron-accepting units on one side and electron-donating units on the other, enabling the simultaneous storage of both positive and negative charges in a geometrically defined arrangement that keeps them separated long enough to drive catalytic reactions. This addresses at the molecular level exactly the same problem that the electrolyzer synthesis plant combination addresses at the industrial scale. Semiconductor-based photocatalysts, particularly nanostructured titanium dioxide, bismuth vanadate, carbon nitride, and perovskite materials, are being developed in parallel. These materials can be synthesized cheaply, are chemically stable under prolonged illumination, and can be engineered at the nanoscale to optimize light absorption, charge separation, and surface catalysis simultaneously. Progress is rapid, though the gap between laboratory demonstration and commercial scale remains large. A solar fuel complex of the future. A fully integrated solar fuel production facility of the future might look something like this. Covering several thousand square kilometers of high-radiance desert, solar panels continuously generate the electricity and feed it to an adjacent grid of PEM electrolyzers. The electrolyzers produce a continuous stream of green hydrogen, which is compressed and piped to a central synthesis complex. On the same site, a direct air capture facility draws atmospheric air through banks of solid sorbent contactors, binding CO2, which is then thermally released and compressed into a pipeline feeding the same synthesis complex. In the synthesis building, hydrogen and CO2 are combined over Fischer-Tropsch catalyst to produce a mixture of synthetic hydrocarbons, which are distilled and hydrocracked into specific fuel fractions: kerosene for aviation, methanol for shipping, diesel for heavy transport. The fuels are loaded into tankers and pipelines that supply airports, ports, and distribution networks, indistinguishable from those that handle fossil fuels today. The water produced during fuel synthesis and CO2 capture is recycled back to the electrolyzers. The heat generated by the exothermic synthesis reactions drives turbines to produce electricity for the CO2 capture and compression steps. AI-controlled optimization systems continuously adjust the balance between electrolysis, capture, and synthesis to match solar generation variability and downstream fuel demand. The entire facility is powered entirely by sunlight. Its inputs are sunlight, water, and atmospheric CO2. Its output is liquid fuel. Its emissions are negligible. This is not science fiction. Every component of this system exists today. The electrolyzers are commercial products. The CO2 capture technology is demonstrated at scale. The Fischer-Tropsch synthesis is a century-old industrial process. The challenge is integration, cost reduction, and the scale of capital investment required to build the first generation of full-scale facilities, whose costs will in turn drive down the price of the second generation, as has happened with solar panels, wind turbines, and lithium-ion batteries before them. The sun has been fusing hydrogen into helium and radiating the energy outward for 5 billion years, and will continue to do so for 5 billion more. It asks nothing in return. Learning to run our civilization on that freely given light, by closing the carbon cycle, using the atmosphere as a carbon commons rather than a dump, and replacing the geology of fossil fuels with the chemistry of solar synthesis, is perhaps the most important engineering challenge of the century, and one that the science increasingly suggests is within our reach.